Yeah, I see you requested to talk.
Okay. What's it like it's all right. What's going on? All right. I want to give everyone a couple of minutes and see if they can get ready to go. Meantime. All right. Well, we'll go ahead. We'll get started. Getting into.
Hello?
Hey, what's going on, Torin?
Yeah, I was trying to figure out how to get this audio to work.
Oh, there. Yeah, there we go.
I was trying to figure out how to get this audio to work.
Yeah, no, you're good. It mutes you when you come in at the beginning.
Oh, okay.
Yeah.
Yeah, I thought something was going on. I didn't know.
I just set it up that way. That way, when y'all join in, you don't have to worry about, if something goes on in the background, you can just click to unmute and if you got anything.
Okay.
Yeah, makes it a little bit easier.
Yeah.
So, let's see. Was that you that texted me?
Yeah, that was me. I was see, yeah, I thought something was wrong or something.
Yeah, no, you're good.
Yeah. Okay.
Okay, so we'll go ahead and get started. Going over chapter 10 today. So
Okay. Got my book.
yeah. So following along in your book, I mean, you'll see at the tops of the slides different titles and everything like that it goes along with sections in the book. So that's the easiest way to really just follow everything along.
It says safe driving mode. Like, how do I get out of that? 'Cause I'm not
Are you driving?
even. No.
I don't know.
Yeah, I don't even know how I got into that. Hold on.
Let me see if I can find something on the app. I don't know. Da-da-da-da. Okay, where's the settings maybe?
Okay, wait, can you hear me right now?
Yeah, I can hear you right now.
Okay.
Yeah.
I think I'll just leave it for now because I
Okay.
don't even know how you mess with it.
Yeah, I gotcha. All right, so going over chapter 10, again, we got control systems. The basically we're going to be talking about a lot of different things: contactors, relays, overloads, stuff we watched videos on last week. I sent out a bunch of stuff going over the different types between contactors and relays. I hope at this point it's pretty clear what the difference is between the two. But we'll talk about how we use these controls and why we choose to use these controls versus, some other method to have our system, operate properly. So these controls are easiest because, oh, excuse me, too much seltzer. All right. All right, where's that? We got a lot of different things. We'll talk about overloads, talk about components, so definite purpose device, all sorts of different things. So first one, and this is one you guys, I'm going to try. I'm thinking, I was talking to Mr. Halloway about it, and I got to get it scheduled and everything like that. But between y'all in the afternoon and my evening class, starting at 6 o'clock, I'm going to see if I can get it where I can get lab time basically right at the end of your class, around 4 o'clock-ish kind of thing. And then I'd be at the school until probably around like 7 or 8 is what I try to do to get groups of labs in. It's just working theory right now, still trying to figure it out. But if I can get 4 hours of lab time between y'all and other classes and everything like that, that'll make it nice and easy to get you guys familiarized with all the different components and working on them with your hands, getting to be able to like actually use your meters and screwdrivers and wire cutters and strippers and everything that I want you to be able to do. As far as contactors go, we are going to get more in depth as long as once I get a definite schedule down, because that's the whole thing is they're just trying to make it where it's
Yeah,
very, very, yeah, they're trying to just control everybody,
yeah, I understand, but at the end of the day, it's like this is not. I know I signed up for it, but like I'm not good with the computer or the phone, so I'm not like even with my midterms, like I just didn't know how to get to them. I thought I started taking it, then it locked me out. It's just confusing, so I'm gonna have to talk to somebody at the school because this I'm not good with the emails. I don't know whether to go to Zoom or in my email. I'm just not used to. I'm not good with that stuff. So it's been real hard on me. I know I missed both my midterms or whatever. It's just real confused. I got a lot going on with my home situation. So this I need to talk to somebody.
Yeah. Definitely try to I'll talk to I'll send an email over to the dean and everything and see if she'll
All right, they can reach out to me.
yeah, she can reach out to you and
Uh,
try to figure something out.
all right, go ahead with your lesson.
Yeah. All right. So contactors, they're going to be the main thing that we have controlling our high loads in our system. So our the compressor, which is going to be drawing the most electricity in an HVAC system. As far as for a residential or anything that's moving refrigerant around, it's going to be the compressor. To control that, we use a contactor. It's a big, bulky block that allows for power to pass through it, and basically it acts as an automatic switch. That switch is either going to be in a open position where the wires are disconnected, and we'll have it where there's no power. Power is just sitting on this end. But because there's no connection, there's no power going to pass through. Once it makes contact, which is why it's called a contactor, you're going to see that's when the power is actually going to pass through to the other side of it. Now, how it operates is you have it where there's a set of contacts on either end, and it's just two pieces of metal, basically, all right? And they're going to be conductive metal, so something that can carry electricity through it, but they're not going to meet in the middle. Instead, what we're going to have is above that, we're going to have mechanical linkage. And that's going to be another piece of metal that is sitting above our other two contacts, that mechanical. So our contacts are lower two pieces of metal. We've got our mechanical linkage sitting above that. And then as the metal mechanical linkage is pushed down, because it's got a spring in it behind it, as it's pushed down, it'll complete the path between our two contacts, allowing power to pass through, just like we would have with a switch. So when we practice with switches on resistance, and you guys saw that, if we have the switch in a open position where it's disconnected, it's going to read OL or infinity. And then if it's in the closed position, it should read close to 0 or very, very low amount of resistance. The problem with a contactor is when it's normally operating, it's not going to be, there's going to be power present. So that's the biggest difficulty with it. With power present in the system while we're testing a contactor, that means that we cannot have our meter set to resistance or ohms. If we set our meter to resistance or ohms, and then we use it on a system that has power passing through it, that will destroy your meter. It will damage it very, very badly. So do not, if there is power present, do not test with resistance. For the contactor, what we're going to test is with voltage. Right? So there's a couple of different things that we're going to see with voltage as far as switches are concerned and how they operate. If you have a switch and it's open, all right, so we've got it where it's disconnected, power sitting here, there's nothing on this side, all right. Now, where I can test to check for voltage is going to be on these two leads right here, on the two ends of the switch, all right. Inside is where it controls whether or not this actually closes. But basically, these two ends are where I'm going to test it. Now, your meter, you have to understand, is not going to test for true voltage at the source. What it's looking for is a root mean square, true RMS. So you're going to see on pretty much all professional meters. It should be on y'all's meter. Should be something that says that. And those will have it where it's got more components to it. It's going to be able to read, instead of true voltage, which would be this weird peak amount like 197 or 175 volts. What it's going to do is it's going to read about 70% of the voltage, and the meter's got two leads, all right? The meter is going to read the difference of voltage between the first and the second lead, which means if I have, let's say, a light bulb, all right, and I've got it wired up, and I've got power coming into it, and it comes in the light bulb, and then it comes out neutral. So I've got power coming in, goes into a bulb, comes out, and I've got neutral. All right, with that, you have it where if I checked voltage on that line coming in and put both my leads on that line, I would read 0 volts because there's no difference. It's just the same piece of wire carrying the same amount of electricity from that point to that point. But when the voltage is starting, and then when it goes through that light bulb as a load, and it comes back out as neutral to head back, all right? If I check on both sides of the light bulb, so my power and my neutral, there's now a difference of electricity, because some of that electricity in between those 2 points is being used by the load, by the bulb. And so now my meter is going to read that difference in electricity, and that's when it's going to read something like 120 volts. Okay, so for a contactor, we test it with voltage. What we're going to see is with an open switch, you're going to read what's called source voltage. All right, so source just means, is it line voltage or is it control voltage? Whatever the source or the starting voltage for that component is. So for a switch on a wall, all right, for a light bulb or for a ceiling fan or whatever it's going to be in a house. All the outlets in a house are 120 volts. All the switches in the walls are typically 120 volts, and that's it. If I have a switch and it's open, all right, and let's say my ceiling fan was off, and I was to read that switch, I would check one side of the switch and the other side. I would check power coming in and then power going out to my light. Because there's a break in between the two, it's just like when there was a load. Now there's a difference. This side has nothing going on. There's no power getting to my ceiling fan. And this side has got power just waiting to go right to that fan. So that difference in voltage allows you to read on an open switch 120 volts. When it closes and I turn my ceiling fan on, now from point A to point B, there's no load. There's no difference. It's just letting power pass through. So I should read 0 volts. We're going to get some testing to see how you guys can, actually see and look at the components and see what happens when you're looking at an open versus a closed switch, an open versus a closed contactor, everything like that. Testing to make sure that a contactor, its whole job is to close and let power pass through, or to open and disconnect power. That's the only two types of contactors you're going to have. They're either used to connect power or disconnect power. And understanding how to read that voltage is important. So you're going to have one lead as your power coming into your contactor, and the other lead is going to be your power coming out, going to your load typically. So going to your compressor, going to your condenser fan motor, going to your blower motor, whatever it might be. The difference of voltage between those two sides can be determined just by putting the leads pretty much on the bottom and top of the contactor on the same side. Because most contactors you guys are going to see and what we're going to work with are what are called dual pole or double pole. There's different terminologies and everything like that. Your book goes into detail showing you diagrams and everything of the different types of contactor symbols and different types of contactors as far as single pole, single throw, double throw, all of that kind of stuff. I'm also going to send out some stuff later today. I got to get it all for email format because I did have it as like a printout, but now I'm going to try to have it basically as a something I can send to y'all, because it was just like a piece of paper I just copied all the time. I don't know where I got it originally. But it goes through like all the different wiring diagram symbols for contactors, because depending on the style of contactor, it might be a different symbol, depending on what its job is, what it's supposed to do. But these are going to be our main way that we can control that load. That's the biggest thing about it. So you've got, again, set of contacts are going to be opening or closing, make or break. And then the armature is going to be that section right in the middle that's moving up and down. Now, typically for your contactor, so that's your armature right there in the middle. Contacts are all these connections right here on these sides. Now, the ones that aren't your contacts are these two leads where these are coming in over on this side. Those are not part of your they are part of your contactor. They're not your contacts though. These are your connections to your contactor coil. This guy right here at the bottom. All right, so if we throw electricity, all right, power comes in, let's say through this lead, it's going to go down underneath this, it's going to go through that coil, and then it's going to come back out. Now, that's going to create a load. So now I'm going to see a voltage difference. If this is working, I should see 24 volts typically for control voltage. Sometimes you will have coils that run on 120. that's what you're going to see between this lead and this lead will be 120 volts. It's usually with much larger equipment. But the 24 volts that we're looking for is going to let us know that, yes, it's getting power. And when it gets power, what's going to happen is that little coil of wires turns into an electromagnet. And you can see the springs right here and right here. And they're going to be, and this metal is going to be pulled in, right, against those springs, is going to be pulled down because of that magnet is so strong. It's going to pull the metal down, and then now we have a complete path across here and across here, right? So the main thing is you can have it where, like it's saying here, with the coil, it's either going to be 24, that's typically for residential. You're going to see a lot of 24 volt coil systems that pretty much, I've never run across a high voltage contactor coil in a residence. The only time I've seen 120 coils is used on commercial rooftop package units. And then the 208, 240 is when you're dealing with more of your commercial, industrial size kind of stuff, large commercial, not just, oh, we've got a package unit on the roof and it's, for one office building, as opposed to, hey, we've got a whole processing plant or a massive office building that's, 18, 20 stories, something like that. So we've got a lot of different approaches that we can have with the contactor and everything. And it's a very versatile tool. It's very easily used for controls. And they're cheap, typically. They're not really expensive. For residential use, you're going to replace the whole thing if it goes bad. For industrial, you can still have where you can buy just the armature. You can just buy the contacts. You can buy replacement coils. You can basically rebuild the whole thing part by part if you want to. But for residents, I mean, they cost like $20 at most. And yeah, it just makes way more sense to just buy a new one. It's cheaper, it's easier, as opposed to, you could probably find a little, this little part right here, this little contact end. You could probably find that coil and all that. But the time it would take you to take it apart, take it off the old contactor, put it on the new put that new part on the old contactor, and then reinstall it, connect all your wires again, you'd have wasted enough time that it's like, well, I could have just taken all the wires off and put in a brand new part for $10 more parts cost, but $20, 20 minutes less of labor time. And our labor is not cheap when it comes to HVAC. Typically, it's going to be very expensive. So the more labor time you can save a customer, the more money you're saving them in the long run. Plus, I mean, with this, replacing the whole part makes sense because you're going to have it where you have a brand new part. You're not going to have it where it's, oh, well, yeah, the contacts are old and worn, the armature's, kind of clunky, but we got a brand new coil on it just the other summer. It's like, that's not worth it. Just get a whole new contactor. So again, the contacts, that's what we were looking at right here on the ends of the contactor. You've got your contacts, and that's what's going to allow for power to be coming in and going out. Now, checking your voltage on your contacts is important. It's, when it's an outdoor unit, you're going to have your power coming into an outdoor disconnect box. Out of that disconnect box, it's going to go right into the bottom of the contactor. That's the next spot it goes. So if you check and you've got 240 volts at your outdoor disconnect, and then you go to your contactor and you've got 120, you've lost 120 volts between your disconnect and your contactor. You've lost voltage. You got to go find out where or why or how did it get away. Usually a damaged wire. It's damaged wires, it's fuses, it's stuff like that. That's super simple and basic, but it happens all the time. It's the stuff that really goes bad is the stuff that is under constant pressure to maintain and maintain safety and maintain a safe operation of the system. If you've got a fuse that's been dealing with high amperage on a regular basis, and now we get a thunderstorm comes in or an extremely hot day, now that fuse is already worn down, and now it's just popped right away. So it's not going to help anyone out. But the contactor contacts, these are really where you can test you're going to test your high voltage side of things, where you're going to test that load voltage and make sure is the power actually passing through to your different loads? Is the power even coming in to your system? You know, at this contactor, the contacts you've also got, besides the high voltage ones, you've got your low voltage, connections to your coil, and that's going to be reading usually 24 or 120, depending on what kind of control we got. Again, coil rarely becomes weak except from excessive friction. Again, coils usually it's a few things going on with them. Most of the time, if they're getting voltage, they're going to work. It's no doubt about it. If it gets voltage, that coil is going to energize. It's going to pull down that armature, and it's going to let power pass right through it. The problem with the coil that commonly occurs that I've seen is that coils become open. When it's a bad coil, it's because it's an open coil or a shorted coil, which you can check if you turn the power off and you look for resistance. If you see OL or you see infinity on your meter from what you're testing from one side to the other of the coil on those two leads, if you read OL or infinity, it's an open coil. There's somewhere in all those windings, a wire disconnected. The other thing that can happen is a short, where the coil starts sending power instead of just through that coil. Part of that coil frays out, hits either the edge of the wall of the contactor, something like this metal right here. You can actually have that energized with 24 volts. I've been shocked by that before. That was one of the ways I found out when I went to a house and they were saying, oh, our AC is not working. I go outside and I'm like, oh, outdoor unit's not working. Well, let me go check the capacitor, because that's a really common problem in the summertime for outdoor air conditioning units is bad capacitor. And capacitor's good. So I'm like, all right, well, looks like the contactor's getting 24 volts. And then I touched it, and right here on this base right here where the coil was touching, I got a little tiny shock. I was like, okay, that did not feel like 240. Otherwise, it'd be flown back. Definitely felt more like 24. Felt like that little tiny voltage. So sure enough, disconnected my power, and I checked for continuity between my leads going to the coil and then the metal of the base of the coil and everything like that wasn't making contact, and it was. And so it's just basic stuff like that. The big thing is really looking at your contacts, making sure they're not, corroded, making sure they're not worn down or anything like that. Make sure that the connections that are on them are tight. Make sure you don't have where it's a loose connection that's just slipping off or, halfway on there kind of thing. Make sure it's all the way on. The mechanical linkage in the center, there's a couple of things that can happen with that. Main thing with that is going to be looking for burrs, or not burrs, burn marks. Sorry, burrs are going to be what you look out for when you're doing ductwork or metal ductwork. You're going to look out for burrs so you don't get them in your skin. You're going to look for these metal burn marks, basically, or black little charred marks. What happens is, all right, little piece of metal sitting right across, voltage on this side, no voltage here. All right, who here has ever flipped a switch when it's really dark inside, and you've had it where when you flip the switch, you can actually see the spark behind that wall plate? All right, that's what's happening under this armature, under this mechanical linkage every time that air conditioner comes on. Click, burn. As soon as that happens, this little guy is going down. Now, if it has dust, debris, bugs, mice, any sort of fur or gunk caught up in there, that's going to build resistance. Not only that, it's going to make it so that we don't have a clean contact. When that armature doesn't come down perfectly flat on it, if it comes down just a little bit of an angle and then hits, when it hits that little bit of an angle before it flattens out and makes that perfect connection, that's when you're going to see that spark like you would in your wall switch. That spark is going to lead to some major problems. That's what's going to cause those burn marks. The other thing that's going to cause is something called arc welding, right? If a system does something we like to call short cycling, where it tries to come on multiple times without any safety kicking it off or making it go into a delay or anything like that. The system just kick it on. Nope, didn't work. Kick it on again. Nope, didn't work. Kick it on again. Nope, didn't work. It just one after the other. All right. Very, very bad thing to happen to a system. When that happens, though, the contactor will be open, close, open, close, open, close, open, close. When it's doing that quickly, what can actually happen is with that spark, it can get so hot, that metal, that it welds, it arc welds is what it's called, and the contactor remains closed. And there you have it where, oh, I wonder what's going on with the air conditioner. It doesn't seem to shut off for like the whole day. And that's when people start calling and saying, hey, my AC is not going off. It's not turning off. It's just on all the time. And that's a really common problem with contactors is that arc welding. And even if it's not, short cycling, it can still have arc welding occur just because wear and tear over time. If the contactor's not cleaned on a regular basis, if you're not making sure that there's no debris, if you're not making sure that that outdoor control panel and access panel is protected. One of the easiest ways, super low cost, I never charge a customer for it. I kept a box of mothballs in my truck. All right, kept them in the back of the truck, always had them. I went out to the unit and I knew they're out in the country, or if I pulled the cover back on the outdoor panel and it's just filled with bugs or gunk, I'd stuff a couple mothballs down in there. Because the access panel on the outdoor unit is not going to transfer any smell into the house. So I don't have to worry about, the house stinking up my mothballs. All I've got to worry about now is, oh, okay, sweet. I get to keep the mice, get to keep the bugs. All that stuff is going to stay away from my electrical components. And that's where we have to be, hey, let's go that extra step, do that one extra thing to make sure that that system not only is operating, but when you leave, it's going to continue to operate without, needing as much maintenance, hopefully. Hopefully, when you go on a maintenance call, now, not always going to happen. You're going to have those calls where it's just, I'm going to be back out here in a week, and I know it, because a customer doesn't want to get the repairs that you've suggested, or they, do want to get the repairs, but they don't, but your repairs are like, hey, we're going to replace everything. So it's just a lot of work that you're going to have to do, ordering parts and all that kind of thing. But yeah, you got it where that's one of the big things is just going that extra mile with customers really is what can set us apart. And, let them know you do that. I don't just do it without them knowing, like what's the point at that point? I had a guy one time and he had, his whole outdoor unit, the access panel was just filled with stink bugs. And luckily they were all dead pretty much because they've been electrocuted to death. But I pulled back the panel. It was just carcasses and shells just falling out of the thing. And I let him know. I was like, hey, look, you had a ton of stink bugs. And I showed him because I swept them all up, put them in a trash bag and everything, took them out for him. And he's like, oh, dang, I didn't realize I had that many. I was like, yeah, there was a lot going on in here. If you have problems in the house, like, none at all. I was like, okay, well, I'm going to put a couple mothballs in the outdoor unit to help prevent that from happening again. That way they don't, gunk up any of the electrical parts. He's like, oh, can they do that? I was like, yeah, that can become a major problem. So, if you start seeing them around the unit or anything like that, keep an eye out. That right there, that dude wanted me out there every time afterwards to be his HVAC guy. Wish I hadn't done that because he lived out in the middle of, oh, Lord, like middle of nowhere. I drove 2 hours to get to his place. It was the weirdest road ever. It was like straight country, and well, not straight. It was a windy country road the whole way, and then out of nowhere, you're driving for like 40 miles, and all of a sudden you come across this like town with 2 giant traffic circles. But it was a weird, crazy thing. But going that extra mile, that's what got me to go out there on a pretty regular basis. So, just keep that in mind always when you're making friendly with customers. If they're way out there in the boonies, and you're not out in those boonies, maybe, don't treat them like crap, but don't make it where they think you're going to be their regular guy. It just sucks sometimes when that happens. Because if your main location where you're working is the other 2 hours away, it's like, okay, why am I going out for this one person? Unless I'm trying to build my business out in that new area, if I'm trying to expand or something. Okay, relays, same exact thing as a contactor. Same exact thing. There's nothing different between a relay and a contactor except for one thing. A relay can only handle small loads. So blower motors for residences are one of the most common spots you're going to see a relay used. Inducer draft motors for a residence are going to be another common spot you're going to see a relay used. Most commercial motors are too large to use a relay on, so you don't see them too often outside of residential. All right. Excuse me. So we've got it where it's the same kind of thing. Instead of being contacts and a mechanical linkage we can see, it's more or less sealed up inside of this whole relay here, and this one really is completely sealed inside of it. There's typically a wiring diagram on the tops of these. On this one, there'd be one on the side of it explaining what each of the contacts is for. These ones are the ones I've used more often. I've seen it where it's, it's these four connections right here, 1, 2, 3, 4. Those four all can connect to a coil that's down here on the bottom. All right. Again, it's a 24-volt coil, and it's going to be moving electricity from, this side where it comes in to this side where it can go out. Inside of here, we've got the same kind of mechanical linkage. It's just smaller. It's contained in plastic, or it's contained in thermoplastic, or some sort of, I've seen it where it's clear, I've seen it where it's brown, I've seen it where it's black, and all sorts of different colors of plastic casings. The main thing is, because of that, the only way we can test this is we're not going to be able to visually inspect these as much for that mechanical linkage. We're going to have to actually test and see, okay, what's the voltage coming in? What's the voltage coming out? What's the voltage across from one terminal to the other? Are we having power pass through or not? So again, fan motors, some condenser fan motors, damper motors, definitely. You've got it where they use relays sometimes for the starting capacitor to make sure, because that's only going to be operating when the motor first starts up. So you have it relay, kick on, turn on the start capacitor. Okay, we're up to speed. Turn off the start capacitor. Relay disconnects, and it makes life really, really easy. So relays, again, it's the same thing as a contactor. It's just smaller. That's the big difference. Now, overloads, these are our main way that we're going to protect a motor and make sure that it is not just operating, but that it's operating under safe conditions. With a
hey, Mr. Marshall.
Yes, sir.
Or Mr. Williams. Yes, sir. Could you go back to that last slide right quick?
Yep.
I'm gonna screenshot it so I can.
There we go.
Thank you.
No problem. So, overloads, most common overload in a system. The most common.
Hold on, I didn't get a screenshot just
Oh, you
yet.
didn't get it? Oh, come on, man. The most common overload in a system is going to be a fuse. All right. Now, a fuse is a one-time safety. That's the downside of it. You've got it where.
Okay.
Get it?
Thank you.
All right.
Yeah.
So the fuse is a one-time use. That's it. That's the downside of it. Because it's one-time use, that means if it's used, then we've got to call someone out to repair it or fix it. It's not going to be something that, oh, we flip a switch or we wait for some time, or oh, let the engine cool off or the motor cool down and then it'll be fine. No, this is going to be, it's going, it's it pops a fuse, done. It stops. Now, the reason why we have it where a fuse is used as a safety is as our last resort. That's one of the ones that really, if there's something majorly wrong with the system, if there's something really messed up, something that's pulling up way too much power where we're going to damage the electrical and the rest of the house, we could damage the breaker panel, or we could just run up the electric bill forever because the system, let's say if it was stuck on or something like that, that's when you can pop a fuse. And that's when it's going to say, okay, well, shut it down because obviously it's not working properly. So let's get, another, let's get someone out here to look at this thing, So fuses, you're going to see them typically in disconnects are one of the most common spots. The other spot you're going to see a fuse most often in a home is going to be in the control board of a system. There's going to be control boards typically on the indoor unit and the outdoor unit, and both are going to require a fuse typically. Now, the type of fuse is what's called a blade fuse. If you Google that, if you look online, you can find a blade fuse picture of it. You've probably seen them before if you've ever worked on a car or minor electrical stuff or anything like that. They're very, very simple. It's like two little teeth and then this little zigzag piece in the middle. And on the top of the fuses, it'll actually have a number. It'll say 3 or 5 are the most typical for HVAC controls. 3 amp or 5 amp is what that means. The big thing with a fuse is you never want to upgrade the size of fuse. All right. For a system, always check the manufacturer, see what they recommend or what they had in there originally, you know, if you're not 100% sure. But you do not want to upgrade the size of a fuse for a control board because that's going to void a warranty, first of all, and then secondly, it's going to be causing problems for your system as far as the controls continuing to operate under unsafe conditions. Blade fuses, you've got them where they can be for automotive and stuff. They go up to like 50 amp I've seen and 60. So they've got plenty of them as far as sizes are concerned. What we're typically talking about is 3 and 5. The easiest thing with that though is instead of getting a bunch of 3 amp or 5 amp fuses, they've got a resettable fuse that you can buy called pop-up. And that is the easiest thing in the world for diagnosing low voltage electrical problems. We have it where you would hook the pop-up fuse in the same spot that you would hook in the regular fuse, and then if the fuse pops, it'll just pop up a button. If the amperage gets too high, but if it has it where the amperage is low enough, it'll let power continue to pass through until you find what your issue is, and that helps a lot because replacing fuse after fuse after fuse is just a waste of time, and it's a waste of money and supplies that you don't need to be doing. So there's that. We've also got brass fuses that are used for our outdoor disconnects, and that's another way we're going to see it. The big thing with it for a fuse is it's going to be rated for amp draw, right? When it sees a specific level of amperage for an extended period of time, or for some of them it's going to be for a short period of time, that will tell that fuse, as soon as that amperage goes through there, basically it's such a thin amount of wire and connection and conductor on the two sides of the fuse. There's a thin little amount of conductive material between the two ends of it. And that thin material, if it becomes where there's too much amperage going through, it literally disconnects it, fries it, it breaks it open, and it pops the fuse. You'll actually hear it if you pop a fuse while you're standing next to it. You'll hear a literal pop, and it's really, really loud, and it hurts your ears like, oh my God. Depending on it scares the Jesus out of you too, especially because if you're popping a fuse, that means you have live power to the system right now. So you're putting the disconnect in, your hand is right here, fuses are right on the other side of it, and then right there you get a big shock as far as a spark and visually, and then you're going to see and you're going to hear that pop, that really loud pop, and that's just annoying as hell. So we have it where fuses, again, most common way we're going to protect the system, and it's just to protect it from amperage. Excessive amperage will lead to excessive power going into our system, and it will fry itself out. So to prevent it from doing that, we have, hey, let's put in these fuses. They'll pop if we overdraw on amperage. If that happens, a technician can go out and check out the motors and see, okay, why were they overdrawn on amperage? Maybe it could be the start winding is starting to go on a compressor, all right? Well, that's easy enough fix. We put in a new starting capacitor. We install one that might not have ever had. And that kind of connection and those kinds of tools make it so that, okay, because the other option is if I don't have that fuse, and that compressor keeps drawing higher and higher amperage, then by the time I get out there as a technician, I'm being called out there because the AC is not working and the compressor is completely fried. It's gone. It's done. And now they've got to get a new air conditioning system. But because of that fuse, now I've got it where instead of a new air conditioning system for $10,000-$12,000, the customer is going to be out, maybe a couple $100 for a starting capacitor kit with a relay or something like that. That's really all it would be. So we'll continue this again. We're going to start at let's see what time is it now. It's 2:15. I wanted to start at 2:30. So yeah, we'll start at 2:30. We'll finish up these slides and everything like that. And then again, as always, I'm going to upload these onto YouTube and then send out a link. So if you want to reference back to them or anything like that, you're more than welcome to do so. All right. Thank you, gents.